Hello friends, welcome back to my YouTube channel. Uh, Today in this video I'll be continuing my discussion on uh, tall columns, design of tall columns, and this will be part number 6. And in this again I will be continuing my discussion on analysis of stresses induced in the wall of a typical tall column. And this time I'll be talking about stresses that are induced due to seismic loads. In my earlier videos, I have discussed stresses induced due to various loads like internal pressure, external pressure, or vacuum, then various dead loads, wind load, eccentric loads. For those of you who have not yet seen my earlier videos, I'm giving link to those videos in the description section. So today I'll be talking about stresses that are induced due to seismic loads. So these are important for those columns which are erected in places which are prone to earthquakes. So in those cases you will have to consider all those stresses that may be induced due to seismic loads. So let us begin the discussion. To start with, let us understand what are different loads that need to be considered while designing a typical tall column. So loads due to which stresses are induced. What are these loads? So you have internal pressure, external pressure, or vacuum. So I have talked about this in my earlier video, one of my earlier videos. You please go and watch that. Then you have due to these loads, that is due to internal pressure, external pressure, or vacuum, longitudinal stresses may be induced, or rather they are induced, and circumferential stresses, they are also induced, that is hoop stresses. So their nature is they are tensile and compressive. So due to internal pressure, external pressure, or vacuum, you can have stresses in axial direction and you can have stresses in circumferential direction. So accordingly, you have longitudinal stresses, circumferential stresses. They are tensile, their nature is tensile and compressive. Then there are certain dead loads associated with a typical tall column. They are also responsible for stresses in the wall. These are longitudinal or axial stresses, and their nature will be compressive. This will be compressive stresses. Then due to wind loads, again longitudinal or axial stresses will be induced. They are tensile and compressive. Due to eccentric loads, again longitudinal stresses are induced, and their nature is, these are bending stresses. Seismic loads, again axial stresses are induced, and their nature is, again they could be tensile and compressive. So today I'll be talking about stresses that are induced into due to seismic loads, stresses induced due to seismic loads. In my earlier discussions I have covered all this: stresses due to internal pressure, external pressure, or vacuum, then stresses due to dead loads, stresses due to wind loads, stresses due to eccentric loads. I have covered all this. Today I'll be talking about stresses that are induced due to seismic loads. So let us understand how to deal with this. First, let us know about the action of seismic forces, how seismic forces are going to act. That will make us to think about them. So if you consider a tall column, I have shown a simple schematic of the tall column. This is the central axis. Okay. Then seismic forces, they produce horizontal shear in a tall column. So under the action of seismic forces, a horizontal shear will be produced in a tall column. Now this shear loading, it acts in a triangular way. The shear loading is triangular. How it is? What is the nature? The apex is at the base of the column. So you can see the seismic load is acting in this way. Seismic forces are acting in this way. So their action is triangular, with base at the with base apex of the column, apex of the triangle at the base of the column. Now, if earthquake produce an acceleration of E, let us say that there is an earthquake at a place where you have a tall column, and if that earthquake is producing an acceleration of E, let acceleration produced due to earthquake be E. If that is the case, then seismic load is given by this equation. Sorry, seismic load is given by this equation. Fs is equal to W by G into A. What are the terms involved in this equation? Before that, let me arrange it like this. Therefore, Fs is equal to A upon G into W. So A upon G I have kept as a one group, and then I have separated W from it. So A is acceleration, G is acceleration, and W is the weight. So acceleration upon acceleration, this will be a dimensionless parameter. So that will be denoted by Cs. So therefore you have Fs is equal to Cs into W. So W is total weight of the column. So here it will be total weight of the column, weight of everything in Newton or kilonewton, whatever may be the case. So W is the total weight. Cs is this ratio. Acceleration A is the acceleration, G is acceleration due to gravity, A is acceleration produced due to the earthquake, due to. So this will have this group will not have any unit, and I'm denoting that group as CS. And what is this CS? CS, they call it as the seismic coefficient. Okay, so due to earthquake, the shear load that will be produced is given by this equation. Fs is equal to Cs into W. W is the total weight of the column, and Cs is the seismic load. Okay. Okay, now let us continue with this. Now we are going to consider, let the height of the column be h, height from the base be h. Now we just saw the shear load that is produced due to seismic forces. Now center of action of this force is located at 2 by 3 h from the bottom. Okay, so if you measure the distance from the bottom, then at a distance of 2 by 3 into h, where h is height of the column, this shear force due to seismic load will be acting. Center of action of Fs is located at 2 by 3 h. Okay, then this force Fs is going to produce a bending moment. A bending moment will be produced about the base of the column, and this bending moment will then be responsible for the stress. Okay, now let us consider a plane that is at a distance of x from the top. Now this distance is selected such that within that distance the thickness of the column is uniform. So I have shown it over here. So we are considering this distance. Then The bending moment at this plane, at a plane at a distance of x from the top, will be given by this equation. ms is equal to cs into w into x square into 3h minus x 3 into h square. So talking about the derivation, I'm directly considering the equation. Derivation, you can get it in one of the book on design of equipment for chemical industries. So for time being, what is important for us, we need to know this equation, because that will be used in calculating the stress that will be produced by seismic loads. Okay, so ms is cs into w into x square into 3h minus x divided by 3h square. Again, you know w is the total weight of the column, cs is the seismic coefficient, and the other terms that are involved, h is the height of the column, and x is a distance that we have selected uh, for our analysis. So this equation gives us the bending moment. Now this bending moment is going to produce the stress. Okay, so h is column height, I have already told you. Okay, now the bending stress due to ms, and that is bending moment, is given by this equation. FBS is equal to 4 ms divided by pi into di plus ts into di. So there are a lot of terms in the denominator. You have let us understand the terms involved. ms is the bending moment. We just saw the equation. It is cs into w x square into 3h minus x divided by 3h square. So if you use this equation, if you use equation for ms over here, you can get this equation. Simply the equation for ms is used over here. So ultimately you will get FBS, that is bending stress due to seismic forces, that is equal to 4 into cs into ws into x square into 3h minus x divided by 3 into pi into di plus ts into di into h square. Okay, so this is how you can calculate the stress that is induced due to seismic forces. So with this, I end my discussion on stresses that are induced due to seismic forces in the wall of a typical tall column. Thank you for being with me. Thank you for watching my video. Please do watch my earlier videos. Please subscribe to my YouTube channel. You tell your friends to subscribe to it, and be with me for knowing more about chemical engineering. For now, have a nice day. Bye bye.